This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio brings you relevant and detailed discussions and interviews on software engineering topics every 2 weeks. Thanks to our audience and the partners listed on our website for supporting the podcast. Hello listeners, Markus here. I wanted to ask you a favor. We're looking for somebody who helps us get rid of the spam on the website. You might have noticed that the comments on the SE Radio website are full of spam. Some of it, bunch of strange Chinese letters that you can't even read. Others seem rather sensible, where the comment kind of takes into account, although it's spam, it still takes into account somehow some of the keywords of the episode, but then there is still a spam link. So we're looking for somebody who helps us get rid of this stuff. Let's call this person the de-spamifier. This is your chance to contribute to SE Radio. Your job would be to basically subscribe to the comments feed and take a look at the comments, and if they're crap, go to the website, log in, and delete it. And you would obviously do us, and especially the community, a great favor. So if you're interested in helping us in this respect, send an email to team@se-radio.net. We'd obviously greatly appreciate your help. Okay, that's all I wanted to say. Let's go on to the content of this episode.
Welcome to a new episode on Software Engineering Radio. Our topic today is the difference between software engineering and computer science. On the microphone is Michael, and my guest today is Chuck Connell. At SE Radio, we noticed an article at the Dr. Dobbs journal on this topic, so we contacted Chuck and asked him whether he would volunteer for an interview on the same topic. Chuck, welcome on the show.
Thank you. Thank you very much.
Would you like to briefly introduce yourself?
As Michael said, my name is Chuck Connell. I work in the Boston area. And I have been working in computer science and software development for about 25 years. As a combination, I have kind of a foot in the practical applied world. I am a software developer. I'm a software consultant. I've worked in a number of technologies over the years, as well as I've been involved in the academic world of computer science. I have a graduate degree in computer science from Boston University, and have continued to take courses over the years beyond that degree. So I've always had an interest in the kind of the theoretical academic world as well as applied programming topics.
In your article, you state something along the lines that software engineering doesn't really fit into computer science because it's inherently different. It's too soft, it's too unpredictable, it has no sound theory around it. How would you summarize your statement in that paper?
Yes, I think what you said is accurate. Let me give a little background on that. There is some attempt by some researchers in software engineering to make software development, software engineering more rigorous and provable and provably correct than it is now. I mean, as everybody knows now, software development projects, sometimes they go right, sometimes they go wrong. Sometimes they finish on time, sometimes they take 5 times longer than we thought they would. And so obviously it would be a great thing if software development were more rigorous, more well-defined, if we developed code in a more provably correct way. That would obviously be good for everybody. So there are some researchers in the field who are trying to make software development more mathematical, more rigorous, and that's sort of the background of my article. And in my article, I argue that while some aspects of computer science certainly are useful to software engineers, and that a good software engineer should know some of that background, that in the end, software development is never going to be rigorously provable. And the reason is that people are involved in software development and are a crucial part of the software development process. So it will never be rigorous and mathematical like some other areas of computer science are.
Now, I could challenge, so why did you even expect to be provable, to be predictable as the other disciplines within computer science they might be?
Well, the answer to that is that there are some efforts, certainly not by everyone, but by some people within the software engineering field to do just that, to define rigorous methods of software development that do make it provably correct. And formal development methods is one way. There's a link in my article on Dr. Dobbs' journal to some good information from the U.S. government agency NASA. I believe it's at Langley Air Force Base, and there's a link in there to some of these formal methods. Another buzzword people might have heard about is clean room engineering. So there are efforts to make the whole software development process correct and provably correct. So my article is responding in a sense to that effort.
So do you believe in clean room development and those formal methods? I remember, for example, the specification language set from my studies.
I believe in them in a sense. I believe that any software development method, clean room, formal, agile, extreme, whatever you want, that they are all useful in the right context, applied to the right projects. But I do not believe in, to answer your question, Joy, I do not believe in formal development methods or clean room in the sense that they can ever give us what they promise, which is provably correct software. I don't believe in them in that sense.
At least not at a reasonable scale. I would expect that it works for some tiny examples, but not really for any realistic application as we know it from our desktop PCs, right?
Absolutely, I agree. Sure, we can define an example of some small program we want and express it in some rigorous semantic language and develop a provably correct piece of software for it. Sure, it'll work on some example, but I claim it will never scale to real examples.
Was there any trigger, any event that led you to writing this article? Or was it just, well, I had planned it for years and now I just do it?
I guess there were two triggers. The first is kind of for years, as I said, I've kind of had a foot in both worlds of practical software development as well as academic computer science, and it always was frustrating to me, and it's frustrating to many people that when you work on a real software project, it never goes as nicely as formal computer science. For instance, I'm thinking, say, of analysis of algorithms, for instance, or cryptographic analysis. Those are areas where you get provably correct results, and or some areas of compiler theory, for instance. And it's always frustrating for everybody developing real-world practical software that it never goes that well. And bugs come up, and it takes longer, and so there's, I and many other people have frustration that practical development doesn't go as well as theory sometimes. And then I guess the other kind of short-term trigger is I was having a conversation. I cite him in the paper with a one of my professors, Stephen Homer, who is a theorist, who is a formal computer science theorist, and we were talking about the difference between practical software development and regular computer science theory, and that kind of triggered the article that I wrote.
How would you separate actually the two topics from each other? Thinking about it, I see them intermingled in many aspects. Can you draw a clear line between both topics?
Yes, I think I can, and there's actually a diagram in my article that makes this point.
Brief note, we include that in the show notes.
Sure. I believe that the difference between practical software development and formal computer science, and that really includes all the areas of formal computer science, is the fact that software engineering and software development involve people in their process. And what we study in school as traditional computer science does not crucially involve people. And I'm looking at the diagram from the article, which I understand is in the show notes. So for instance, areas of computer science such as queuing theory, algorithms, machine learning, complexity, network analysis, those topics do not involve a person crucially in the subject matter. I mean, people study those subjects, but they are true or correct or not correct regardless of a person being in the middle. Whereas at the top of the diagram there, subjects such as usability, requirements engineering, scalability, estimation, design patterns, those topics crucially involve people. You cannot study those topics without studying the people that are involved in the software process. So I feel that, in my opinion, that's the bright line between what's traditionally considered software engineering and what's traditionally considered computer science.
Could you maybe go one level deeper?
Sure, I have some examples. Let's make it concrete with two examples. The first is the problem of estimating in software development. Every real software project, other than some small piece of homework we're doing in a class, every real piece of software development, we want to estimate how long it's going to take, because if the answer is that it's going to take a week, it's going to take, say, one person a week, we'll say, sure, let's go ahead and do it. If the answer is that it's going to take 20 people 5 years, we might say, no, that's not worth it. So estimation is crucial in every real-world software project. I mean, we need to know how long software is going to take to decide if it's worth it or not. And estimation, by its very nature, means how long are people, this team of people, going to spend doing this project. And I claim, and I think it's self-evident, that there's no rigorous mathematical method or recipe that we are ever going to have that's going to produce accurate estimates for how long some team of people is going to take to do some piece of software. I mean, even imagine that you have a crack team that has turned out many good software projects before, let's say a team of 10 people, but partway through the project, 5 of them get sick or lose interest in software development. Well, your estimate is out the window, and no formal system can capture that. Now, I should add, with an estimation, there are some fairly well-developed estimating techniques, such as Kokomo, and I think I have a link in the article about that, that try to apply some formulas and mathematical heuristics to estimation. But if you look close, and they have these very complex, daunting formulas that look very scientific, but if you look closely at that work, it's really still a guesstimate. I mean, those formulas that are involved there are based on previous projects by similar teams and can easily go wrong. And the formulas even involve all sorts of scaling factors that are extremely subjective. So these seemingly rigorous estimating methods are not, if you look at it closely, are not as rigorous as they appear. So I think estimation is an area where I claim there will never be a rigorous, provable, exact method for doing it. The other example is what is often called modifiability or maintainability or extensibility. I'll kind of lump those all together, those properties of software. We want software to be modifiable because we think of a new feature or we change an existing feature. We want it to be maintainable because there's going to be bugs to fix, and extensible, we want to add some new feature or scale it in some way. So this is surely a property that we want out of any real software that we care about. But the question of how maintainable, modifiable a piece of software is crucially involves the people who are working on it, because if you have a bug to fix, what do? Well, you sit down and you look at the software and you try to understand what's going on there and understand what's causing the bug, or if you know what's causing the bug, you try to understand where the fix needs to be applied. Well, that's a human process. And I can't imagine any formal system that's going to tell us how to construct software so it looks more clear to the people who have to maintain it. It's just crucially kind of bound up with the way people think. So to me, that's another example of where formal systems will never give us everything we want in software development.
Another example you mentioned in your article is CMMI, the Capability Maturity Model of the Software Engineering Institute. Well, at least what I know about it, you get a number out of it. So how can you come up with a number from something that is not really touchable, graspable? How do they do that, and what is their trick to come up with a number?
Yeah, the CMMI, I'm actually a believer in that, and let me take that from the other side. CMMI, which is Capability Maturity Model, and there's various flavors of that, comes out of the Software Engineering Institute at Carnegie Mellon University in Pittsburgh. And CMMI actually is not a rigorous method, although it's very long and very heavy when you get the printed version, and can be difficult to read, and some teams of software developers love it and some hate it. But its goal is not to be a rigorous method. Its goal is really to be a set of best practices that have turned out to work well for other teams of software developers. So I actually believe that they're on the right track. They're not trying to be provably correct. The thing is, the text is not filled with mathematical formulas. Again, it is very long. It is very difficult to read in places. But their goal is a template of development methods that have been found to be good, really best practices at a number of previous sites, and they're always tweaking it. They have the right spirit that, they never thought it was correct 20 years ago or 10 years ago. They're always tweaking it and always learning. So, I think they have the right spirit, although it's gotten kind of big and onerous.
You mentioned now several times the word best practices. For example, in the context of patterns in software design, you mentioned it for CMMI. So it seems like best practices is the middle ground, as good as it can get with software engineering to make it somehow structured.
Yes, I think that's right. I think that, middle ground is the right word. We don't want to say there's nothing we can ever learn about software development, and every project is something new from scratch, and we have no idea how to do software development. Well, we clearly don't want to say that, and that's clearly not true. On the other hand, I maintain in this article that we can never make software provably correct. But the middle ground is just what you said. Patterns of software development that have been found to work well on past projects. And patterns also, when you read that literature, patterns work well for certain kinds of programs. And patterns always say where they are applicable, where they make sense, or they should say that. And so patterns are kind of best practice. And patterns can apply at kind of at the code design level or higher up at the architecture level. And the idea is the same. It's best practices, things that have been learned on previous projects. CMMI is that as well. Agile techniques, extreme programming, those are, again, best practices that have worked well in the past, that have a good chance of working well on your new project, especially if you understand what kinds of projects they should be applied to. So I think that's the right way to look at software engineering, to instead of trying to develop techniques that are provably correct, which I maintain will never work, we can learn, we can develop wisdom and best practices over time.
So is that something like a conclusion, or what do we learn now after we observe this difference between computer science and software engineering, this difference in matter, in behavior, in structuredness, in predictability?
Yes, I think the difference is, let's take a topic like, cryptography, or say register allocation in compiler theory. You can get correct results in those areas and for those questions, or at least for some of those questions. In software engineering, I think correct results are nearly impossible in every situation, unless you define the problem very, very narrowly. But what we can get is best practices, body of knowledge built up over time, experience that works well going forward.
Can we get better at that? Should we get better with that? Do you know, or do you see any holes where we don't make the best out of what we have today with software engineering? What would be your recommendation?
Well, those are good questions. I guess there's kind of two parts there. Can we get better? Absolutely. Look at other areas of engineering, such as bridges, bridges over rivers, and rockets, space rockets. Those areas of engineering, they get better all the time. Occasionally there are failures. You still see bridges that collapse, but people have gotten better at that, every year, more or less, as time has gone on. And the same thing with rocket technology. And I certainly expect software to continue to do that. I think the whole area of patterns is a fairly recent area in software engineering, and a lot of good has come out of that. So I think that, I think we certainly can get better. Any holes? That's a good question. I have to think on that a bit. Are there areas where there are still holes in our knowledge? I don't know. Good question. I don't have an immediate answer on that one.
You mentioned that software engineering or software development is an engineering discipline. Now, if you would have to decide between the terms science, art, or craftsmanship for the act of software development, what would you relate it more to?
Craftsmanship. I imagine, for instance, a skilled woodworker, a cabinet maker. Someone who is a good woodworker certainly knows the technical details. They understand the materials involved, the wood, the tools, the way the tools and the wood and the glue and the materials interact. They understand structural engineering of putting together something with wood. Those things are absolutely required of a good craftsman. But craftsmanship also involves more than that. It's experience built up over time. It's a sense of the artistic, a sense of design that only people can understand. So I like the term craftsmanship for good software development.
Yes, I totally agree. So I like to challenge you on that, and so that is a typical question you would ask at a beer in the evening with some friends, together with some geek friends, and you could get lively discussions on it. But as you said, I believe it's the experience for one. Which really helps in developing good software, reliable software. And the other part that I think is important, there's also some beauty and simplicity in it, as with craftsmanship. I mean, you can solve and create any kind of thing, but it also matters how you do it, how this piece of wood afterwards looks, whether it looks like a chair or something that you hardly can identify as a chair, but you might potentially be able to sit on it.
Right. That's right. And in fact, this sort of touches on something we talked about in our email before this interview, which is education. In the ideal world, how should software engineers be trained? What should it look like to go to school to study software engineering, software development? And I think that, in my opinion, software engineering development should be more than a subset of computer science. I mean, a good software developer absolutely needs to know some computer science. They need to know analysis of algorithms. They need to know complexity. They need to know programming language theory. Absolutely, there are areas of formal computer science that a good software engineer should know. But that's not the whole story. And software engineers also need to know management techniques, how to work in teams, a little bit of psychology, user psychology, as well as team psychology. So in my ideal world, software engineering would be taught not completely separately from computer science, but recognizing that it has a different focus.
Making it a first-class citizen at university,
right.
Actually, and
right.
Not somewhere hidden in any CS department. Yeah,
that's right. That's right.
I agree with that. I mean, I remember saying me that in one of the earlier episodes, but I really believe good software developers don't just come easily out of computer science studies, but there needs to be more on it. Either have a really strong education on software engineering, gotten that during your studies at university, or really do a lots of practical work to learn on it and to get experience and knowledge on it.
Right, and that's right. And I think both are needed. I mean, I could imagine somebody, for instance, who is very, very good at formal, say, complexity theory, analyzing the complexity of some algorithms, or looking at the mathematics of what's computable and what's not computable. I can imagine somebody who's very good at that, but is not a very good software engineer because they're not good at communicating with users to understand what they want, or not good at working in teams. And I mean, we need people, of all types. And on the other hand, a software engineer does need to know some of the rigorous theory as well. So, there's an overlap, but they're different skill sets.
Now, we talked a lot about education at university. How about really the application of software engineering in industry, in daily life for building real world products? Do we need to change something after this knowledge, after this observation?
You're thinking of how sort of ongoing education for people who've been working in the field?
Ongoing education, or do we treat software development right in industry today in general? I mean, looking back at your experiences from IBM or other big, large companies.
I think part of the answer is that if software development were taught, as we're both suggesting, more as a first-class citizen, more as its own discipline, I think that would help. I mean, what happens now is that many people doing real-world software development have a computer science background, a computer science degree from somewhere. And again, that's valuable and that helps to some extent, but I would like to see software engineering curriculums include more than just that, and I think that would help going forward. And I mean, one view of computer science that I partly believe is that computer science, core computer science, really is a branch of mathematics. Now, I mean, I didn't make that up. I'm quoting something I've heard there, and I think there's some truth to that. And and that's interesting and that's valuable for people who want to study that. And I've studied those subjects and I've enjoyed them. But, we should recognize that, doing real world software development is more than just a branch of mathematics.
So do you have any other related discussions or recommendations on literature and ideas around that topic? You sent me in advance a set of links which we all will include in the show notes. But any recommendations on interesting topics from you?
Let me just mention those links briefly, what people can find there. And so the article I wrote that prompted this podcast is there. And Grady Booch, there's a very interesting site there. What he has done is collected interesting software architectures. And I think this is the kind of thing that people use as an input to design patterns. But his goal there is to kind of build up a shared knowledge of the way people have approached difficult, interesting software projects. Steve McConnell, who wrote Rapid Development, as well as After the Gold Rush, and several others, he's a very well-known author in software engineering. His blog is listed there, and there's a lot of good stuff in there. Also, the page from NASA about formal software methods is there, and that's interesting to look through. And I think you've also posted my website called beautifulsoftware.com, where I've collected my essays on this topic and others about software development.
What kind of essays? Now you made me curious.
Well, I've been writing for a number of years about software engineering, so there's this article as well. There's another piece that I just finished and will come out in Dr. Dobbs this month about refactoring. We haven't talked about it yet in this broadcast, but the whole refactoring movement, and I kind of summarize what that is and talk about some background theory for refactoring is there.
So this month is September.
Yes.
In case we publish this episode later.
Fine.
In
yes.
September.
My understanding is that piece will appear during September on Dr. Dobbs.
September 2009.
September 2009, correct. And I wrote a number of pieces about the process of open source development, which is also listed there. And had an online debate with Eric Raymond, who's well known in that field, about the process of open source development, and that material is on that website as well.
Okay, lots of interesting links and things to look at. Any final comment from your side?
I think that just about covers it. I'm always interested in hearing from readers or listeners, with their comments or links. I've over the years I've been writing, I've often improved an article or tweaked an article based on some feedback I got from somebody. So, I welcome people to give me feedback. My contact information is on that site, beautifulsoftware.com.
And also, please use the comment feature at our SERadio.net
Absolutely.
comment infrastructure.
Okay.
All right. Thanks, Chuck, for this interview.
Thank you, Michael.
Bye-bye.
Bye-bye.
Thanks for listening to Software Engineering Radio. Software Engineering Radio is an educational program brought to you by Hillside Europe. If you want more information about the podcast and all the other episodes, visit our website at se-radio.net. If you want to support us, you can donate to the SE Radio team via the website, or you can advertise for SE Radio, for example, by clicking on the Dig Reddit Delicious links and the /dot button. To contact the team, please send email to team@se-radio.net, or if it is specific to an episode, please use the comments facility on the website so other people can react to your comments. This episode of SE Radio, as well as all other episodes, are licensed under the Creative Commons 2.5 license. Please see the website for details. Thanks to Charlie Crow and the Podsafe Music Network for the music used in this show. The song is called Vegas Hard Rock Shuffle.